Hello, I'm Kenji at the University of Tojo. In this talk, I will present our latest research titled Stealth Shaper, Reflectivity Optimization and Surface Stylization. This is a joint work with Ariel Shamir at the University, Bernd Bickel at ISTA, and Nobuyuki Umetani at the University of Tojo. I'd like to give a quick note before moving on to the talk. Although we will discuss stealth designs, we weren't sponsored by the military. We take these designs as an inspiration that drives our creative 3D modeling research. With that stated, please enjoy the talk. Let me begin with the background of shape modeling via computational optimization. Working on graphics, we see a variety of interesting 3D shapes daily, and many of them arise from the optimization of certain physical functionalities. In fact, our graphics research community has presented various algorithms for modeling such functional 3D shapes. Among these physical functionalities, the reflectivity of a surface poses interesting design problems. For example, an optimized 2D panel can create intricate caustic effects. Also, reflectivity matters for more general 3D surface design, like architecture. For example, a certain building shape is known to accidentally concentrate sunlight, causing undesirable glaring and heat problems on the street. Another reflection property I want to introduce is the one called stealth property, which is commonly seen in the design of fighter aircraft. Stealth aircraft hides from radars by minimizing ritual reflection, which is a reflection back in the incoming light direction. What makes stealth shapes particularly interesting is that they show an inspiring relationship between geometric style and physical reflection property. Interestingly, stealth optimization consistently results in a unique style of geometry with sharp creases. That means even if you don't know how these shapes were optimized, you might have seen the visual style of stealth shapes. Or you possibly know the style from more artistic contexts, like modern architecture design and concept sci-fi spaceships in games. In this work, we leverage these inspirations about geometric style and reflectivity. And we will use the inspiration to derive our reflection-aware surface modeling tool that can overcome tedious trial and error processes in manual workflows. So, at the highest level, our goal is the reflectivity optimization of 3D shapes. Our framework takes a general triangle mesh as input, and the user specifies desired reflectivity objective. Then our method outputs a shape that significantly improves the specified reflection function, only causing minimal modification to the original geometry. More specifically, we formulate the reflectivity objective as a scalar energy function E, which is computed by simulating the reflected radiance L, which is the intensity of light, for the points on the input surface and varying incoming light directions. We then minimize the energy by computing its gradient with respect to the input mesh. The gradient is obtained using the differentiable rendering technique that in a sense computes the gradient of radiance. This is the high-level overview of our method. But before describing our algorithm in more detail, let me briefly discuss the strengths and challenges of related techniques. The first is differentiable light transport. In computer graphics, light transport simulations based on path tracing have been used for realistic rendering. More recently, researchers have studied algorithms to backpropagate the gradients of light transport, like neural network training, to solve inverse rendering problems. This framework is very powerful and is able to handle various objective functions involving light, including hours. But unfortunately, optimizing a mesh is a delicate task. In fact, carelessly updating vertices using their gradients can easily cause unacceptable distortion to the mesh. To make matters worse, light transport gradients typically contain noise due to stochastic Monte Carlo integration. So, to enable our application, we also need a strong shape regularizer that can keep the geometry during the reflection optimization. But what would be a good choice for the regularizer? A natural first attempt would be as rigid as possible deformation or ARAP, which has been used in many graphics applications such as animation, geometry processing, and fabrication. ARAP deforms the shape by minimizing an energy function, which encourages the rigid transformation of local neighbors. This ARAP framework could be incorporated into our optimization iteration as a geometric regularizer. However, the original ARAP is not suited for our optimization because it's often too restrictive. For example, ARAP keeps a round surface round, which cancels new geometric features like sharp creases, crucial for stealth optimization for instance. We observed that a naive ARAP regularizer, when directly plugged into our optimization, can eventually result in large unnecessary deformation. There is a very inspiring work that addresses a more flexible style of geometry achieved by ARAP. Liu and Jacobson allow the user to specify target normal directions to achieve various geometric stylization effects. They minimize the ARAP plus normal constraint to align the initial normal to the target direction, which creates a funny cubic stylization effect like this. However, to apply Liu and Jacobson's method, we first need to specify the target normal directions to achieve the desired style. This is prohibitive in our application because we want to optimize reflectivity, which can involve complicated effects like multiple light sources, shadowing, and interreflection. Therefore, we don't generally know what the optimal target normal should be. In summary, our framework has two core components of reflection optimization and shape preservation. Existing techniques are good at one of them, but do not work well for the other. To overcome this situation, we present a new optimization scheme that effectively combines the two techniques. Here is our approach. We propose integrating differentiable rendering and ARAP-based surface stylization into one alternating scheme for reflectivity optimization. The essence of a technique is the shared target normals, which allows us to seamlessly combine the two sub-steps. The first step is gradient-based target normal optimization. In this step, we fix the geometry and update independent variables t for surface normal using the gradient of the energy function. And the second step updates the shape using optimized normals as the target style. This way, ARAP can find a nice shape-preserving deformation that also optimizes the specified reflection function. Finally, let's look at some of our results. Our full optimization has coarse and fine stages and a parameter controlling the strength of regularization. In any case, our optimization converges with about 90 iterations, which roughly takes 3 minutes. And here are some of our stealth optimization results. Interestingly, the optimized shapes have successfully reproduced the stealth style with sharp creases. But the question is, are they really stealth in terms of the minimized ritual reflection? To test this, we conducted a real-world measurement with our 3D printed models. For the experiment, we set up a coaxial light source and sensor to achieve parallel incoming reflection directions, and a dark tunnel to exclude other possible light sources. And we put a rotating stand inside the tunnel to see the object from the optimized circular directions. And the result looks like this. Actually, where you're supposed to see is inside a red frame, although it's the most boring black square. But that's a good thing, because it suggests our method has successfully minimized the ritual reflection of such a very complicated shape. Also, here's a measurement in the top light environment, in case you don't trust me that there is an object. Importantly, our framework can also handle other reflection properties by slightly modifying the energy formulation. To demonstrate this, we optimized the sunlight reflection by the building to create desired daylighting environments on the street. And we also tested the results via fabrication. Now let me briefly wrap up the talk. In this work, we study computational reflectivity optimization of 3D shapes. Our algorithm uses target normal to effectively combine differentiable light transport and ARAP-based geometry regularization. We 3D printed stealth and architectural models and showed our algorithm can effectively optimize the specified real-world reflection function. If you're interested, please see our paper for further details. This is the end of the talk. Thank you very much for your attention.